Hey y'all, welcome back. Second video of lecture 7. And in this video, I'm going to talk about sort of the discount rate in a little bit more detail and compare it to the interest rate and also introduce slightly different notation using the discount rate that's going to be useful when we get to some actual problem solving in later videos. And so, as I sort of alluded to in the last video, there is a tightly interlinked relationship between the discount rate and the interest rate. And so many of you are likely familiar with interest rates, right? If you put your money into a bank, for example, today, you should expect to have that money plus whatever interest it accrues over time, right? And so if a bank gives you an annualized interest rate of 2%, which is super high right now, especially when there's a lot of quantitative happening in the US, um, then you would get for $100 investment into a bank today, you would end up with something like $102 in a year from now. It's not exactly that calculation because they use compounding of interest, but that sort of is a marginal point in this context. And so, how do we think about discount rates now in this context? So, the discount rate and the interest rate are typically used interchangeably as the same, like the rate itself, right? But their interpretations are different. And so it depends a lot. It depends primarily on how you want to understand the value of some amount of money today in the future. That would be the case of the interest rate, or the value of some future amount of money today. That would be the case of the discount rate, right? So if I give you $100 today, and I want you to tell me how much is that $100 worth a year from now, you would say, well, it accrues this much interest, and so I have $100 plus whatever interest I accrue. But in the case of a discount rate, it's more like saying, I'm giving you $100 a year from now. What is that amount of money worth in today's terms, right? And it's worth less than $100 because whatever I put into the bank today, right, will accrue interest, and then I want it to give me to end up with $100 a year from now, right? So it's sort of just a flip flopping of the way in which we interpret the horizon of money being earned or outlaid, right? So if I'm giving money now, that's an interest rate story. If I'm getting money later and I want to know the value of it today, that's a discount rate story. And so, um, if you remember back to the question I asked you in the beginning of the first video of this lecture, which was if you were offered $100 today, how much would you need to be offered to wait a year to accept the money, right? $110, 20, 120, 200, right? How much money? If the economy-wide interest and discount rates are equal, right, which they should be, then the answer you give to this question should be the same as how much interest the $100 today would accrue over a year, right? So um, if your discount rate is 5%, then that's like saying the interest rate is also 5%. So if I put $100 in today, I should end up with $105 a year from now, is the same way of sort of saying I'm indifferent between $100 today and $105 a year from now, because that's sort of the time profile of how money grows in our economy. Okay. So that's sort of some more information and more context behind how discount rates and interest rates interact with each other. The second part I want to introduce is thinking about it's more notational than anything. And so sometimes you're going to see problems that feature the discount rate, which is that delta that I wrote in the last lecture, and that's the delta you see right here, versus the discount factor. And a discount factor is just a mathematical like transposition of the discount rate. It's just a different term using the discount rate versus just using the discount rate on its own. So the way we write the discount factor is this rho, that's what this P here looks like, is 1 over 1 plus the discount rate, right? And so um, if the discount rate is 0.05, which would be 5%, then the discount factor would be 1 over 1.05, okay? And it may not seem clear, like, why do we need to have this convention? Why can't we just use the discount rate in these problems? I think it'll become much more clear in the next section when we actually do some problem solving using the discount rate. It basically allows the notation to be a lot cleaner um, while getting the exact same answer or desired output from our calculation. And so that's what we'll be talking about in the next video. So I'll see you guys then.